Hi there. I want to talk about epoxides as a functional group. Basically how we make them and just kind of the things that we can do with them. Now, in some of my other previous videos, I think we've already seen the formation of epoxides. I just want to remind you again about how we can change a molecule that looks like this into an epoxide. So if we use a strong base, and typically the example of this would be sodium hydride. Why? Because sodium hydride is really nice because when it removes this proton over here, we get this O minus. And it does it in an irreversible way. So it's great. It forms hydrogen gas, which then disappears. So we get this O minus. And then the O minus can close in and kick out the bromine as a leaving group. It's a SN2 reaction. And so when it does that, we will get an epoxide. And it can only do that because it must be an SN2 reaction. And so the bromine has to be on the opposite face. So we're going to get a molecule that would look like this. This is an epoxide. I've exaggerated the fact that it's on the top face over here. But for those of you who think about this carefully, this molecule over here is not actually chiral. There's a mirror plane through the center here. So whether it's straight up or straight down, it wouldn't make any difference. I only do this because of the fact that when this closes in over here, I have this pointing up. So of course this, I can't even write racemic there because it's not even a chiral molecule. So we need to know how do we make epoxides. And of course, if you follow things, we can actually make this from the original alkene. So cyclohexene, use it as a simple example. If we treated this with NBS and water, and we'd have some solvents present as well to make sure everything was soluble. So DCM would be okay. Doesn't mix very well with the water, but we could also probably use THF. So we could do this reaction, and this would form this molecule over here, which is our bromohydrin. So we've added a bromine and a hydroxide at the same time. And then we could then use a base to form the epoxide. So that is an easy way of forming epoxides. But what I want to introduce to you now is a better way, because we can just do this in one step. And to do that, we use a new reagent whose abbreviation is MCPBA. MCPBA. Right. What this does is it immediately puts on this epoxide in one step. It's a great reagent to use. It's a solid, stable solid that won't explode. That's an important feature of reagents when I choose them, is that they're not going to explode. This sort of reagent, it's perbenzoic acid. So let me draw it out and I'll show you where this acronym comes from, and you'll understand it. So the M is actually standing for meta. So this molecule looks like this. It's got a chlorine group on the benzene ring. And then this looks like a carboxylic acid, but it's not. It's a perbenzoic acid in that it's got two oxygens. So it's the type of peroxide, which is at this point over here. Its full name is metachloroperbenzoic acid. And we can see here the MCPBA part over there. And this reagent is probably one of the nicest ones to use for making epoxides. This is a very electrophilic molecule. This oxygen over here, it might not appear to you, but I'm going to show you the mechanism. But that oxygen over there is extremely electrophilic. And so when we have a slightly nucleophilic alkene, we can get this reaction to go. So let's look at the mechanism. It's really easy, but there's a lot of kind of weird arrow pushing. Not so weird. I'm drawing it in this way just because of what I know, how the mechanism is going to go. So what happens is that this pi bond over here adds to the oxygen that is very electrophilic. And at that point over there, this bond can break, and it's electrophilic because when it kicks in like that, it's resonance stabilized. But what happens is this pi bond is going to kick back out onto the oxygen, and of course the lone pairs can pick up this proton over here, which means that these electrons over here can kick back in and effectively add to one side of the one of those two carbons. So if you compare this reaction compared to the brominium formation, bromine was just one atom that added on, but bromine could only form one bond. Oxygen can form two bonds. And in this reaction, it's losing these two bonds, or disappearing, but it's forming two bonds to the carbon atoms. And so we get this epoxide forming. And the result over here, if you draw this out, is just the chlorobenzoic acid. And being a carboxylic acid means that we can easily remove this from the reaction in an aqueous worker. At base, it'll deprotonate it and it'll wash out in the aqueous layer. So a very useful reagent for adding epoxides to alkenes. I want to show you this reaction just to show you and just an important consideration to think about with alkenes. You probably heard about this a long time ago, and I just want to kind of point it out to you again. We've spoken about how alkenes could be di-substituted like this. And this one is tetra-substituted. It's got 4 different alkyl groups on it. And it turns out that tetra-substituted alkenes are a little bit more reactive because of the inductive effect of the alkyl groups. There's a slight kind of push of electrons in towards this alkene. This one has 1, 2, 3, 4, whereas this one over here only has 2 that would push in. And we can actually see this if we add just one equivalent of MCPBA. So normally, if we ever see reagents on the top of an arrow, we would assume that they're in excess unless we're told otherwise. But in this case, I am telling you otherwise. So there's just one equivalent. And it turns out that when we do this, the major product of this reaction would be where the epoxide has added to the one face. And so I'm just going to draw it in adding to the one alkene and also to a face. So the epoxide over here I've drawn it coming onto the top face. Again, this molecule is not chiral, so there really isn't any considerations revolving around that. But it is one diastereomer. So the epoxide is either facing up, and then the 2 methyl groups will go down, or the epoxide is on the underside face, and the 2 methyls will be pointing up. That is the same molecule, of course, because we just turn it around. But this is the way I chose to draw it as we see it here now. So this kind of shows that this reagent over here is relying on its electrophilicity. In other words, the alkene that is going to react needs to be the most nucleophilic alkene, which is actually that one, which is slightly more substituted. And we get this series of reactivity, which actually applies to all kinds of reactions where we have alkenes, that this alkene is less reactive than having say a trans alkene, which is di-substituted, which is less reactive than having a tri-substituted versus a tetra-substituted alkene. Anything that is putting electron density onto there is going to make it more reactive to this. But also consequently, anything that takes electron density away from an alkene, for instance, a carbonyl, something that looks like this over here, this alkene over here is not nucleophilic. In fact, to put an epoxide over here, we use some different chemistry, which I'm not going to discuss right now. What I do want to talk about, though, is just to remind us of the reactions of epoxides and how they are similar to the reactions of the bromoniums. There are some differences, and so to do that, let me just look at this intermediate over here. I have specifically just desymmetrized it now. So this molecule has the epoxide is sitting on a tertiary carbon effectively, and then a secondary carbon over here. And now if we add a nucleophile to this, where is that nucleophile going to go? And let's just use a really simple nucleophile so we can track things. I'm just going to use SH. It's basically like instead of OH, I just want to use the sulfur so that we can see a difference because this is already an oxygen. The question here is, where is that nucleophile going to add? Now, when we used a bromonium or the mercurinium intermediate, the atom that was here was positively charged. And when that happened, the 2 bonds that were between that atom to all the carbons, were greatly weakened by that. And what tended to happen was the nucleophile would go to the most substituted carbon because that's where the more stable carbocation would be. That was because the bonds to the atom were extremely weak. There's a difference here. This oxygen is not positively charged. It's neutral. And because it's neutral, both those bonds to the carbon-oxygen bonds are relatively strong. The only thing that is in this favor over here for this reacting is that we've got this very strained three-membered ring. All right, whenever you get this three-membered ring in chemistry, it's usually extremely strained, and something just wants to come and break that open to release that strain. And so in this case over here, it turns out that the place that it wants to attack is at the least substituted carbon because it's less sterically hindered over there. And when that happens, the ring pops open and we get what would normally be a terrible leaving group, an O-, but only exists as a good leaving group, O- now, because of this break in the ring strain. And as you can imagine from, if you understand and remember from the brominium and mercurinium intermediates, and this is an SN2 reaction, the SH must have come from underneath. And that means that this center stayed the same, and we end up with a O- over there. And this could pick up a proton, which would typically happen, it might have been part of the solvent, or certainly at the end of the reaction, we would protonate it with a mild acid, so we get an alcohol over there. But look at the stereochemistry here. The important thing here is the stereochemistry is conserved. We get an SN2 reaction occurring at that position over there. Can we get a nucleophile to add to this position, just like the bromonium? Can we get a nucleophile to add there? And the answer to that is actually we can, because we just need to use the principle that we've already seen with the bromonium, which was that the bromonium was positively charged. So all we need to do is do exactly the same thing, but we need to get a positive charge in this oxygen. And the easiest way to do that is to add some acid. If we add acid, we will protonate this, which activates that. And then we can add our nucleophile. Now, just think for a moment here. I can't add SH- as my nucleophile. It's an S-, therefore it's a strong base. So if I have an H+ and I've got an S-, all that's going to happen is the H+ is just going to hit the sulfur. So we do need to have now a neutral nucleophile. So we could use, in this case, H2S. Pretty smelly stuff. And what will happen is that now that we have protonated that oxygen, we have created an intermediate which is just like the bromonium. It's a positively charged atom over here, a three-membered ring. And what's happened now is we've considerably weakened these bonds. And so where the carbocation would form would be the most, or the best place for the nucleophile to add. So 2 electrons, but one of them adds to the bottom over there, and we open up. And so now under the acid catalyzed mechanism, we can get the nucleophile to go to the other side over there. All right. So epoxides differ in this sense over here compared to the bromoniums and the mercuriniums. So in that normally, because they are sort of a lot more stable compared to the bromoniums, we can isolate epoxides, for instance. I mean, they are stable compounds. You can get them and then get a molecule and crystallize it, etc., or have it as a liquid or distill it. Bromoniums, you can't do that. So in this, you can get the reaction will go to the sterically least hindered side over there. We can, however, switch it to the sterically more hindered side if we use the principles of adding acid to create a much better leaving group over here and make it look a lot like the bromoniums. This would be a lot more unstable. Having said that, I do want to point out that this is the general rule, but sometimes these things don't work exactly the way that we expected. But for now, as we're learning how these things open up, this is absolutely what we need to look at.